Our session today is about indirect detection, so take your time. Thank you for coming.
Thank you. Thank you for the kind invitation. It's a pleasure to be here. I was asked to cover, for this first talk of the day, some of the perspective and challenges and status of the indirect dark matter searches. Okay. I won't spend much time about introduction, motivation, and so on. I will say a few words to remind you of the some key elements of the wonderful introduction that Graciela gave us yesterday. And I will define in particular the contours of the bet of indirect dark matter detection, because it's a bet, in fact. And then, rather than giving you a sort of abstract example of the challenges and the type of work that you have to deal with if you are interested in this strategy, I will illustrate the difficulties, challenges, and excitement with a specific example. So I will quickly review the galactic saga, in case you are familiar with that. And then, depending on time, I will go more or less in details about some ideas, some directions for the road ahead, couple of strategies. There are several students in the audience, so maybe it's useful for them to know what I think are the most promising ways ahead of us. And then I will move to the conclusion. I have also a second talk later on today before lunch, and that will be a more specific talk on one strategy, in particular dark matter with antiprotons in cosmic rays, and then I will go into some of the nitty-gritty that you should know if you work on that, okay? So far so good. So what do we know? I mean, the problem is not finding dark matter. The problem is identifying dark matter. This is a big difference. Dark matter has been found, okay? From the cosmological point of view, you have an effective macroscopic theory. This is what Graciela told us yesterday, which is very simple from the macroscopic point of view. You had a stress energy tensor, which is just dust, and this is able to describe from the initial condition that you infer from the CMB, this is able to describe the formation, evolution of structures over several decades in mass. This is a plot of the mass variance versus mass of different structures. It's equivalent to the power spectrum, okay? And you see that this extends from 10 to 22 solar masses down to 10 to 12 at least. Actually, there is a qualitative agreement down to at least 10 to the solar masses, though quantitatively that's a different story. And this is a predictive theory. It's a predictive theory which passed the tests. The predictions were made before the observations, and they were passed. One example is the third CMB peak. Another example is the baryonic acoustic oscillations. The shape, the normalization of all this was predicted, was observed. So this behaves like a normal scientific theory, and no problem with that. The problem arises because there are some good, bad, and ugly aspects of the identification of the dark matter, and the good aspect is that the dark matter requires new physics. This is another information that comes from cosmology, essentially. This does not come from rotation curves or galactic evidence. This comes from cosmology. So this comes from perturbative solutions or exact solution, physics we understand and model very well. So this requires new physics beyond the standard model, and this is the good aspect because there are only a few indications, empirical indications that you need that, and that's why particle physicists are excited about dark matter. The bad is that gravity is universal, and we have inferred the presence of dark matter through gravity only. So we want to infer the properties of the sort of ultraviolet theory, which is reduced to this macroscopic description on large scales, from gravity. And this is basically impossible. Maybe you can do something if you break the fluid limit. This is the example of the primordial black hole case, okay? So that this simple raw field is not sufficient anymore. You have some granularity, and this tells you something about the microphysics. Or you need some other type of identification, some other channel, some other coupling, okay? That's the whole goal of direct searches, collider searches, indirect searches. And I will cover the case of indirect detection, namely remotely sensing the effects of byproducts of dark matter annihilation or decay or some other particle physics process, which yield information about the dark matter nature. Okay? There is the ugly part in this trilogy, and the ugly part is something you should never forget if you work on this field. There is a caveat, and the caveat is that there are models that fulfill all the constraints Graciela told us about yesterday. You know, it's cold, it's white cold, it's relatively collisionless, etc., etc. However, there are models that you can write down where the dark matter identification quest admits virtually untestable solutions. Okay? So we know that we might never know the answer to the problem. So this is a bet. Hope that we can identify, and there is reason to models where this is possible, but don't forget this ugly truth. So let me define a little bit better the contours of this bet, and I will use the example for laziness, just for laziness, the example of the WIMP candidate described by Graciela yesterday. It's not unique at all. Most of the considerations also apply to other candidates. From the cosmological point of view, all these ideas about new physics at the wake scale and maybe some symmetry that you introduce for other reasons, like preventing proton decay in R parity for SUSY, etc., etc., boil down to the idea that you had one particle, say electroweak strength coupling and electroweak scale mass, into the early universe plasma. This particle is stable or very, very long-lived. And what happens then? Well, what happens is that if it interacts with the standard model through some binary interaction, there is a sweet spot. This is the WIMP miracle mentioned yesterday, where you get the right value for the relic abundance for typical electroweak scale coupling and mass. Okay? Now, this is basically, in one slide, the WIMP paradigm, but this has implications. People liked it also because this has implication on the way you can search for it. Okay? So this binary interaction diagram you can read in different ways. Okay? In the early universe, there is the freeze out of this process that is responsible for setting the primordial abundance of dark matter. But if you have sufficiently dense region today, for instance, for the annihilation process, residual annihilation going on, and this residual annihilation may yield some secondary particles, standard model particles, photons, neutrinos, hadronic showers, electron positrons, which are, of course, connected in a specific model. Hence, you have this multi-messenger approach to cross-check any possible excess in one channel with additional channels. Okay? So, at the end of the day, in this way of reading this diagram, corresponds today to the indirect dark matter paradigm for the WIMP. Okay? For other classes of candidates, you can still do indirect dark matter searches, the axion, for instance, but other physics is involved. But what is common, you want to detect stable particles which are remotely produced, say the center of the galaxy, extragalactic space, etc. The injected particles, the standard model particles that you can detect, depend on the particle property. Here is this binary annihilation, and the dark matter astrophysical distribution. So you need to know both. And then particles at the Earth, the stuff that you can typically measure, is affected by propagation effects in general. So you might have energy losses, you might have diffusion, etc., etc. And that's part of the technology you have to master in order to compute this signal. Okay? Now, there are many, many, many channels. In fact, indirect dark matter detection is just a collective name for like well, maybe a dozen main strategies to detect that. So this is for me, it's a very hard task. I cannot really cover all possible way to search for it. I chose a few nice pictures to give you an idea of the diversity of all that, but you have neutrinos at the South Pole, you may have ground-based gamma ray telescope, you have space-based gamma ray telescope that gives us these nice pictures. You may have cosmic ray detectors either on balloon or on the International Space Station. You will hear more about that later. Or you may have probes of the cosmological probes, like the edges for the 21 centimeter or the epoch of ionization in studies. So there is no way I can cover that, for sure not in half an hour. So I will summarize the status of the multi-messenger program for the identification of WIMPs. Conceptually, the strategy is similar to the story of the blind man and the elephant. So these blind men were wise men, were an elephant, and they had the chance to touch the part of the elephant that was in front of them. And so for them, it was like a snake, or it was like a tree, or something like that. And if you collect all this information, you will reconstruct the shape of the beast, and the beast here is the dark matter. In our case, the summary is that there are null results of all these strategies in none of the channels, but there are a number of claims. The bad points about these claims is that none of the claims has been confirmed in another channel. And this is the basics of the credibility of this multi-messenger strategy. 2, for each of these claims, there is at least one competing, more trivial explanation. Okay? So unless these conditions are relaxed, you won't be convinced that you have discovered dark matter. So for us, the story is not about the blind man and the elephant. It looks like the men are not blind, but the elephant is invisible. So that's my summary of the current status of these WIMP searches. Now, what are the practical problems that you have to face if you work in this field? Some of these are shared by other searches, like collider or direct detection, but I think, in particular, the second one is very, very peculiar of indirect dark matter searches. So the first one is that you don't really know the signal. You know, in a parametric way, the signal within some toy model cooked up by theorists. And it's very unlikely that we just got the right model by chance. Okay? So I give you an example. Even if dark matter is explained within a SUSY scenario, it's very unlikely that you have pinned down all the parameters of your SUSY scenario, and so you play with some simplified models, and you cannot expect perfect prediction of the signal. The second is even more serious, that the background is only approximately known. Okay? And sometimes this is an irreducible limitation, because you don't have the ability of going to your lab, repeat the experiment, change the condition, and you have to live with what the nature gives you, the universe that nature gives you. So I will illustrate this with a zoological example. Okay? Let's say that we believe that the background, the signal looks like a zebra. We are looking for zebras. And then we believe that the background is a giraffe. So the typical situation in an indirect dark matter experiment is the following. You build a new satellite or a new telescope, and you start having some preliminary data that look like that. Okay? The typical reaction, hundreds of theorists, run and write papers on the archive saying that we discover clearly dark matter. It looks like dark matter. But then, you start collecting more data, and you build a more complete picture of what's going on. And you discover it. Okay? And this is a giraffe. This is the same family as the giraffe. Okay? So we were not so wrong about the background, but clearly it doesn't look exactly like a giraffe. It's quite weird animal. And it's a metaphor for the typical situation that we have in indirect dark matter searches. We learn about the background, which is in fact astrophysical signals, at the same time as we search for some anomalies. Okay? So I will illustrate with a less zoological and more astroparticle type of example, this type of dynamics. And I take the gamma ray sky. What about the gamma signal that you expect from dark matter? Actually, one simplification of dark matter searches via gamma rays, which is not shared, for instance, in cosmic ray searches, is that energy losses, absorption, and of course deflections are absent for typical signals you look for at least at the GV range. I think there will be an example discussed by Armand where this is not even true, okay? But let's simplify the problem. And then the differential flux in energy and solid angle writes often, not always, in a factorized way, depending on the cross-section, the annihilation cross-section, the mass of your dark matter, well, it's self-conjugate in nature or not, and the spectrum of particles in the final state that depend on your detailed couplings of the dark matter with the standard model. This is a particle physics factor, which in principle, if your theory is perturbative, etc., you can compute and you end up with some prediction for the gamma ray spectra. But there is also another factor which depends for the annihilation on the integral along the line of sight of the density square of the dark matter. So these you have to infer from theory, from simulations, from observation. You have to be creative here, okay? Now, here there are some simplifications, okay? This factorization only holds if sigma v is v independent. Otherwise, you have to make a convolution over the velocity distribution, which is not known. This was mentioned yesterday as well. And if prompt emission dominates, of course this is true. If not, and you have to care about, say, inverse photons from electrons that are emitted in the final state, well, then this is a much more complicated problem. What about the morphology and the dark matter distribution? Do we control this theoretically? Well, this is a typical map obtained for the gamma ray annihilation signal obtained from numerical simulation of a halo from within a halo that looks like the Milky Way. Okay, it's quite old, but the picture is not very different in modern simulation based on matter only. Now, look at the fine prints of that. Of course, here you signal from the galactic center. Okay, this is the galactic center. There is a halo around the center. There are satellites of the Milky Way, and some of these hotspots are actually clusters of the extragalactic sky. And there is also a diffuse bluish quasi-isotropic signal. However, most of this signal depends on structure formation in the nonlinear regime. So there is no theory, first principle understanding of this. This is different from the evidence that we use for dark matter that convinced us that dark matter exists, that explains BAO, the CMB oscillation, etc. First caveat. The second caveat is that this simulation is only dark matter, is containing only dark matter, and a very idealized form of dark matter where each particle is maybe thousands of solar masses, by the way. So, but we know that in the galaxy you have baryons, and actually you even know observationally that the gravitational potential, especially in this inner part, is dominated by baryons. So at the end of the day, you know and you expect that baryons should alter this picture. So you see that when we move to actual surface, the predictivity of our theory is a bit shaky. So we have some ideas, broad ideas, how the more than that. And if you look at more quantitative estimates of the typical uncertainty, for instance, of the brightest spot, this central region of the galaxy, you have typical uncertainties that many orders of magnitude for the intensity. So it's fair to say that we don't know what's the normalization of the signal from the inner part of the galaxy, even if we knew the mass and the cross-section of the dark matter. If you look at the data that a satellite experiment, a satellite gamma ray telescope like Fermi Lat in particular, gives, this is a sky map in the same coordinates, say, and it doesn't look at all like the picture I showed you before, okay? Compare this picture with this picture. So first conclusion, most likely dark matter is not responsible for the bulk of the emission that we see. Without doing complicated analysis. In fact, you clearly recognize the galactic plane emission. This has to do with pi zeros that decay. These pi zeros, mostly, the bulk of it, some inverse Compton, etc. And these are produced by cosmic rays hitting gas producing pi zeros in inelastic collisions. And then there are, of course, point sources, both galactic, mostly in galactic plane, and extragalactic, which are most ones. And of course, this does not look like the expectation. This means you have to understand these backgrounds, which are in fact very interesting astrophysical sources often, in order to try to dig your dark matter signal out of this. Okay, so that's a challenge. And in fact, this challenge has been taken, and many groups over the past decade have claimed and have reported the detection of an excess towards the galactic center that looks a bit like that. And you see that now this seems to resemble a little bit more what we were seeing before in the simulation. And the spectrum is also quite peculiar. It's affected by larger or bars, but it's a peaky spectrum around G-ish energies. And you saw from the photon yield that this you can obtain in dark matter annihilation. Okay? Again, how is this obtained? By subtracting from this map all the known contributions due to astrophysics. So we take a snapshot of the savanna, we remove all the animals that we know about, all the giraffe, and what is left we call an excess. Now, people were very excited about that. Why? Are still very excited. I'm personally very excited about that. Because it seems to match what we expect from dark matter. The spectrum is well fit by, say, a 50 GeV-ish massive particle. The spectrum is quite uniform within these inner 10 degrees of the galaxy or so. And, you know, it looks quite okay with the subtracted excess. The morphology is okay, roughly. Within all these uncertainties that we have, it matches more or less what is expected from the simulation. A bit steeper, actually. And the intensity is also okay for astrophysical standards. You know, this is basically the expectation that we would have from the naive WIMP models, and this is the contours that we have from some fits in a paper. So, not so bad, huh? However, there are other surprises associated with Fermi. It's not that Fermi only discovered this excess. It also discovered many, many, many other things that were not so expected. Huh? So let's take one. Millisecond pulsars, these are fastly rotating neutron star, probably rejuvenated due to accretion of a companion. So what happens for human beings can also happen for stars. You can be rejuvenated if you have a junior partner. They were not known as gamma ray emitters, basically. And since the launch of Fermi here, this has quickly become the dominant galactic class of gamma ray emitters. Okay? So the dominant galactic class of gamma ray emitters was not in the zoology that we had before launch of Fermi. Fine. Can they explain what we see? Well, a good reason why they could is that they exist. If you look at all pulsars in a period derivative of period plane, there is a big cluster here at millisecond pulsars, so no doubt that you have these objects. For WIMPs, we don't know. For millisecond pulsars, they do exist. That's a big important point. The second point is that their spectrum, both isolated objects and the collective spectrum that we infer from globular clusters, look bumped with a peak roughly at the same energy of what we see from the galactic center excess. Okay. Third argument, there have been a couple of papers claiming excess power at small scales, namely that the signal of this excess is not smooth as you would expect from a dark matter distributed smoothly, rather clumps in little excesses. Okay? There have been two techniques applied to that. One is we have wavelet transforms, so basically you detect some excess power at small scales without background modeling. Another one is with non-Poissonian technique, basically pixel statistics. I won't enter into these details. This has been partially retracted in this paper, but actually there is this other paper that says that this is not, there is nothing wrong with that. In fact, it's all expected. And this one and some of the people here are both co-authors of the previous paper. So they even disagree on the robustness of the method. Huh? So, but in any case, this, at least, the current situation is that it doesn't look conclusive. Huh? But forget about catchy titles like Dark Matter Strikes Back. There's no evidence for dark matter from this study. At best, the study is not suitable for finding anything. That's a caveat. So this should be an erratum of the previous paper. At best. Of course, let's play devil's advocate, right? Maybe these are not millisecond pulsar or point-like sources. Maybe this is just the gas, which is much more, you know, it's clumpier than our modeling, which is, okay, it's well possible that this excess that looks point-like is just a mismodeling of the diffusion, okay? Conceptually, it's possible. However, what is surprising that has been revealed also in the last couple of years or so is that the galactic center excess traces stellar density in the bulge. Now, for either dark matter or mismodeling of the background, which is gas, it's very weird that this should follow the star in that environment. So the most likely explanation, of course, this is not settled yet. Huh? It might still be that this is dark matter or a mixture of astrophysical backgrounds and dark matter. Fine. Right now, the most likely explanation in my opinion is that this has to do with some point-like sources, mostly, associated with stellar phenomena. Maybe millisecond pulsars. And there is another argument which is very rare, but I worked out this, so let me cite it. If you just rescale the number of millisecond pulsars which are measured locally. So first, an information. Why is this problem not settled just by finding these objects in the galactic center, say with radio telescope? The problem is that it's a strong selection bias. We can only detect easily millisecond pulsars which are nearby. So we have really no idea of the millisecond pulsar distribution all over the galaxy, in particular in the galactic center. They are too dim, if you wish, to be seen. Now, however, if you now compute millisecond pulsars per unit of solar mass of stars in our neighborhood, and then you say, how many stars do I have in the galactic bulge? You rescale this. Well, you get an estimate of how many millisecond pulsars should be there, which accounts from 10% to 200% of the signal. To me, this is precision astrophysics. That is another independent argument that tells you that probably these objects have a role, at least a subleading role in explaining what's going on there. Okay. There is some hope that future experiments, well, future observation, in particular in the radio band, the SKA in the future, possibly some precursor, can identify some of these objects, probably not very easily in the galactic center, a bit of it, because in the galactic center you have too high ionization, too high density of electrons and too large magnetic fields. So this is very hard for radio techniques to get a clean signal, because this radio, you know, you have dispersion effects, you have absorption effects, and so on. So a little bit set is most likely the good target. And recently we also pointed out that in principle also gravitational waves might give you a hint of multi-messenger cross-check of this signal through a different type of signal, namely the monochromatic spin down of pulsars if there is some ellipticity, as predicted in many models. There is a chance that maybe not this generation, but the future generation of detectors can detect them. Okay? Now, what about the road ahead? What do we expect for the coming years? Clearly, the elephant, the kind of elephant that we were looking for. Okay? So maybe it's a different animal. I can identify two broad classes of strategies that people are following. Doesn't mean that these are correct. So you are encouraged to build up your own idea about that. One is to keep faith. The WIMP idea is basically correct. It's just that we are a bit unlucky. Maybe there is some mild tuning. After all, you know, there are accidentally light particles, we believe, in the standard model. The electron mass is not the electroweak scale. Maybe the BSM particles are slightly too heavy to be produced at the LHC, and there is a hope that extending the energy range a bit, factor 2, 3, might be enough. Or maybe we are unlucky in the sense there are mass degeneracies, and this prevents from easy identification. After all, this is also happening in the standard model. The neutron and the proton are quasi-degenerate, right? So none of this is so too crazy. This is one possibility. The other possibility is that this was a red herring. This WIMP miracle is just an accident. And maybe dark matter is unrelated to the hierarchy problem and this claim that new physics should appear at a weak scale and whatnot, even if it's there. And you should find inspiration in other theories, for instance, neutrino masses, maybe dark matter sterile neutrinos, for instance, axions, and so on and so forth, or phenomenologically driven observations. For instance, there is a problem with the dark matter paradigm at small scales. I told you that the agreement when you go to very small masses is not great. There are difficulties in drawing strong conclusions, but it might be that these observations tell us something about that, the nature of this dark matter. So there are these two strategies. An important comment, however, is that, as Graciela also insisted on this point yesterday, there is no argument from indirect that justifies a pessimism on WIMPs. Okay? We have just started to explore the interesting parameter space. And there are big chunks of theory, P-wave annihilating dark matter particles, which are not basically almost unexplored in indirect detection. The real pessimism in the community is driven by the fact that there is no evidence for this scenario of new physics at a weak scale, which was the theoretical motivation for this. Okay? It's not that we have empirically excluded through indirect detection searches. So still, and I'm still doing it, search for WIMPs in indirect searches. Okay? What is true, however, is that we are more and more limited by systematics. So we're going to try to squeeze the best we can from future observation, but it's becoming harder, okay? So the WIMP searches are not dead. However, the return over investment is diminishing. That's true. You have to work harder and harder to improve less and less in the parameter space. Of course, will be progress. There will be progress, and you can take advantage of the existing or planned experiment. Surveys like the LSST, which will be renamed, I think, or already been renamed the Vera Rubin telescope, can discover hundreds of dwarf spheroids, these satellite galaxies, and then also measure refined J-factor measurements with ancillary observations. And this will alone improve the current sensitivity, which is this black line in the sigma V mass space, by a factor of a few. Okay? Again, are there problems? Yes. These kind of strategies already limited by the level with which you know the background, okay? The line of sight background towards some of these objects. So you can work on some of these strategies to improve over this limitation. We have been recently using some data-driven methods to try to beat these, maybe astrophysical assumptions or model assumptions that you put in. And of course, you will take advantage of future detectors like, say, the CTA, the Cherenkov Telescope Array, and maybe this will test one of these other hypotheses, that we were just a bit unlucky. WIMP dark matter is a bit too heavy to have been detected currently, and maybe there are models with 5 TeV, 10 TeV dark matter, and this will be accessible with this object. Or there will be improvements, possibly there are design and R&D for dense arrays in the neutrino telescopes that can probe the complementary to direct detection, the spin and cross section at relatively low masses. So there will be progress. But maybe this is not the right direction. Maybe it's not a WIMP at all. And actually, if it's not a WIMP, of course you cannot give up on the idea that it's a stable or metastable relic. But you can more easily give up on the idea that this object was in equilibrium in the early universe, in chemical and kinetic equilibrium in the early universe. Okay? If this is the case, it's interesting that, say, LHC has not found any sign of dark matter. Why? Because this is a very rough argument, but basically the same type of cross-section that enter the decoupling in the early universe also affect the number of events produced at LHC. And then if this is very low, not sufficient to bring your particle in thermal equilibrium as well, and then explain two things, okay? So, I'm almost done. So what can happen? There have been directions of study along these lines. For instance, it has been realized that if you have a couple of models, you will hear more about that, so incomplete equilibration, insufficient equilibration, with light mediators exchanging with the standard model. Or another model is cannibalization, where you have 3 to 2 or 4 to 2 processes responsible, so not any more binary interaction involved in the game. Well, these kind of non-thermal candidates can allow you to realize strongly interacting dark matter. Okay, so this is a new feature that maybe you can probe with new type of observables that I have not yet talked about. You know, non-thermal Big Bang nucleosynthesis, modification to the hills of light bonds, or maybe CMB anisotropy and polarization as well. X-rays and Lyman alpha astrophysical observations, and maybe also at colliders and direct detection, depending on the model. This is more model dependent. What's the generic lesson that you learn from all this? Two things. One is that, well, what two things on the slide? The dark matter mass can be much, much higher than what you think. You can easily get dark matter candidates as heavy as multi-PV. For instance, you will hear one example about that. And the best probe of this is through decay in ice cube, for instance, or in the future in high-energy gamma-ray telescopes, 100 TeV telescope from the ground. There is one LASO which is going ahead as far as. Or you can have very light dark matter, sub-GeV, okay? And this may affect cosmology, it may affect spectral distortion in CMB, it may also affect soft gamma ray. And there is a window which is still not open, the soft gamma ray, the MEV gamma ray window, which is basically unexplored. There are proposals for telescopes. And in general, if you are desperate and you don't know what to do, it's always a good idea to do something different. To explore some window which you have not opened yet. An example is the gravitational wave window. Although it's almost ruled out the idea of primordial black holes, but for a small window, the discovery of coalescence of binary black holes has had the positive effect of pushing people to revisit all these constraints and making more credible and robust. And then you have other windows, 21 centimeter astrophysics, the hyperfine transition from the end of the dark ages and the dark ages, which is a possible probe more powerful than the existing one. We did a preliminary study, and other people have done preliminary studies on that. CMB spectral distortions is also another probe. So this is my overview. The traditional arguments related to dark matter, to BSM physics at the electroweak scale, have not led to a discovery yet. The indirect WIMP detection technique have delivered what promised. They have reached the good sensitivity, okay? They are digging into interesting parameter space, and this will be pushed for the next decade or two, but the return over investment is shrinking. There are alternatives, in particular non-thermal related to non-thermal dark matter production mechanisms, which can be implemented in dark sector, can be implemented in super WIMPs, etc., and they can be motivated either by other theory argument, neutrino masses, axion, or you can have a phenomenological argument, disagreement between the profile of halos in the inner regions, etc. A common aspect and strategy is to explore alternative windows for electronics, which is, I mentioned a few, this is not exhaustive, but MEV gamma ray sky, gravitational waves, we just started, you know, the exploration of gravitational wave sky, 21 centimeter, CMB spectral display, advanced X-ray surveys, 100 TeV gamma ray sky, improvement in neutrinos, etc. And of course, this is not, I mean, I had to cover the indirect dark matter part, but this is not disconnected from direct searches and collider searches. For instance, some of these candidates have implications. The light mass frontier in direct detection searches, you may have to deal with long-lived tracks, long-lived particles, tracks and metastable particles and displaced vertices at colliders, invisible Higgs decays, and so on. So the quest is still going on. Thank you.
Questions?
Thank you very much for the very nice talk. I have a question on
Ontology?
Zoology of the galactic center. On the millisecond pulsars, do you